let's talk about learning decision trees. So our goal is that we want to find the smallest or the optimal decision tree that correctly classifies a training set. Unfortunately, this is an NP-complete problem. It's just too computationally expensive, and given the compute we need to put for it, it might not be worth it in the end. If you're interested, you can check out this reference. So if not optimally, how would we construct a decision tree? Typically, we resort to what are known as greedy solutions. And the greedy solution that we'll study here is that we're going to start with the whole training set as well as an empty decision tree. We're going to start off by selecting the best attribute, whatever that means. We're going to split based on that attribute and then repeat over time. Why is this suboptimal? Because it's not really forward-looking. It's just doing the best action at this point in time. Would that translate to the best tree overall? Not necessarily. That's the limitation of having greedy solutions. Okay, so let me give you another example of this here. Let's consider this table of data. We have here two features, x1 and x2, and some output attribute y. And I'm going to give you two potential splits. One split splits on x1 and then goes to the next row, and another splits on x2. And in the second row, you can see that if I split on x2, if I proceed down, for instance, the true path, then in this true path, I'm going to get some number of y's being true and some number of y's being false. Who thinks the one on the split on the right-hand side is a better split? Okay, who thinks the one on the left-hand side is a better split? Who doesn't know? Who doesn't care? Okay, good. You all care. Good. Why is Hamza, the one on splitting on x1, a better split?
Yeah, sorry. Yeah, I think it matches better. Like it seems you can correlate the truth value of x1 to that of y.
Okay, what do you mean by correlate the values?
As in, like when x1 is true, like it seems like you have a bigger influence of x1 on y. Like if x1 is true, proportion, like in terms of probability, you have higher probability of having y true as well, and same thing for false, which you don't have in x2.
Okay, anyone else? Any thoughts? x1, x2 being better or worse, and why? Shima?
The depth of tree will be different by selecting each of this attribute as the node, as the first node.
How do you know the depth? This is only one split and depth 2, let's say. How do you know that depth would be different?
Because the number of situations that occurs in selecting each branch is different in each case, and this makes the different decision tree to be result.
Okay. Is there a particular evidence that you could point to back your argument? Because you're saying that for some reason, did you favor x1 or x2, by the way? Splitting on x1 or x2?
Okay, I prefer x1 as the first node, and because its region, the region with the same label are more compact and
interesting. So Shima is pointing out this part here. She's saying if we split on x1, one of our regions is going to contain instances that already all have the same label. And remember, our stopping criterion was we go until the entire region contains the same label in the case of classification. So we're done, right? We might still continue and split off here, but then that's only half the work to do compared to the one on the right hand side. Whereas if we split on x2, we have a case, sure, that's 75% true and 25% false on the left side, but then 50-50 on the right side. So there's still a lot of uncertainty left in our tree, and we got to keep going. And that might again, it's a greedy approach, right? So we can't be sure optimally, but we need to make the best action at this point in time. And the best action at this point in time tells us that splitting on x1 at least we're already done with one of our branches. Yes? Okay, cool. So I would agree that X1 is a better split because leaves are confident in their output prediction as opposed to splitting on X2. So we're trying to see that after we do a split, we get closer to what is known as a deterministic decision, right? Something closer to being almost certain about what the branch's classification would be. And we'd want to avoid cases where we have a uniform distribution, something like that, where it's still a coin flip at the end of the day. So our intuition is that at each of the splitting steps, we're going to choose the most informative feature right now. And why did we say it's greedy? It's greedy because it's not forward-looking. We're going to optimize for now, but there might be a better split had we done it a different way. But that's an NP complete problem, so we can't really deal with it. Okay, so now let's consider this data here. Let's assume that we've decided already that we're going to split on the feature X1. We're going to call X1 width. And then we need to now select a threshold, right? We need to select one of two thresholds, either A or B, to split. Now, based on the discussions of the previous slide, which seems better, A or B, threshold A or threshold B? Who thinks B? Okay. Who thinks A? Okay, Hamza thinks both. Okay, why?
It tricks me.
Okay. Why is A better, Hamza?
Yeah, I mean, same arguments for compactness. Like, so you pick the one which gives you, for sure, one of the class, like one of the classes, like.
Right, A feels like a better split because the left-hand region is already very certain about whether the fruit is an orange or it's a lemon. So in general, the faster that we can assign a class label and reach a leaf node, the better. So how do we go about quantifying this? This is really about quantifying uncertainty. And if a leaf contains examples with the same class, that's good. That means we have low uncertainty in the prediction. And if a leaf contains examples from every class, that's certainly bad. We're trying to move towards a case where we reduce the uncertainty the most. And so the idea we're going to use is we're going to count at our leaves. We're going to define a probability distribution and use that to define a notion of uncertainty. And to do this, we need to take, it says a brief detour. It's not so brief, but we need to take a detour into information theory. And that's where the introduction of Claude Shannon came in.